Hello, this is the pre-lab and lab evaluation discussion for the ME144L force and displacement sensing and measurement lab. So in this first one, I mean for you to review the strain gauge concepts that are introduced in the lecture slides. And it's important, this lab it does use a strain gauge beam sensor, so you should become familiar with some of the terms. So review the derivation, if you will, of the relationship between strain and strain gauge resistance found in Appendix A. That will show you where the sensitivity for a strain gauge comes from. And I'll just tell you, this is a gimme question here. It's the gauge factor is what I want you to think about. So the gauge factor is what's derived, and remember, the sensitivity is telling you, okay, what change in resistance do I get per unit strain? Okay, so review that, be comfortable with that. So I have a question here about an axially loaded beam that has 4 strain gauges on it. You should look at the bridge configuration table that I've given in the lecture slides. Note that you have gauges 1 and 3 here on opposite sides, the opposite faces, and then 2 and 4. I didn't mention this explicitly in the lecture, but these are only active in one direction. So 1 and 3 are active, 2 and 4 are transverse, so they're not going to see that strain. You're not straining those 2 gauges. So those are the ones that we refer to as dummy gauges, because they're there to really give you a complete full bridge. They're also there so that they're at the same temperature as the 2 gauges, right, that are being strained. That way you get the temperature compensation, right? All of these gauges will change the same amount due to temperature, but only these 2 gauges, 1 and 3, will see the strain. Okay, very subtle, but something that you should be aware of is that's why you put all these gauges on here. So what I want you to do is tell me okay, I have a full bridge here, 2 of them are active. What is the output voltage that you'd expect to see on the output of that bridge if I loaded it with 5 newtons axially, and given these geometric parameters, gauge factor, and individual resistance? So understanding that gauge factor relationship to strain using the basic equations given here, you should be able to come up with that. Okay. Problem 2 relates to the beam mechanics that are relevant to the cantilever beam that we use to build the laboratory setup that you're going to be using. I showed you a relationship between the stiffness of the beam and the material and geometry parameters for the beam. When I say here, I want you to conduct some research to justify that stiffness relation. What I mean is I want you to go back and look at either your studies in a machine design class or maybe in your mechanics of solids course, but somewhere there, and let me just show you what I'd expect you to do. I'd expect you to go find a good reference, and I'm going to show you, this is a nice little handbook, Geik and Geik Engineering Formulas. Either again your book or a handbook. I like this little handbook. It's easy to keep around. And here's one table, right, that shows, for strength top calculations, the deflection of beams and bending. And this very first one here shows a simple cantilevered beam, kind of in the opposite direction from the way I usually draw it. But there's a load W here at the tip. There's you can't see the Y sub M here is the deflection. I'm sorry, this is again not very clear, but you can see. Gives you, this table gives you support reactions, the moment equation, and so on. But the relevant relation I want you to think about is the deflection relation, Y at the maximum point, to the low W. Again, it's kind of hard to see there, but this is the force deflection relation. Is like a spring. So this term here, in the form it's given, that's the compliance, these terms together, right? If you flip that around and send it to the other side, that's and now you have a term here, K times the deflection. That's your force, Kx deflection. That you should think of that as like a spring. So K the stiffness comes from a term like this. This comes from basic beam deflection relations, and that's the kind of review I want you to do. Those are things that I would expect for you to be familiar with from the previous courses. Okay, we're going to use that in another question and in the lab evaluation. Okay. So again, in completing the pre-lab, I would want you to have gained an understanding of how to relate the strain at the strain gauge position, and keep note of the fact that the strain gauge position is not at the ends. It's somewhere within the length of the beam, as shown in the setup, and the force applied, the tip deflection, and the stiffness. All those are interrelated, and you should summarize those for yourself, and that's what this pre-lab question is about. I want you to be familiar with how to use the full bridge configuration, and physically what it means, and that's what this pre-lab question is about. So I want you to sketch a three-dimensional drawing, an isometric, for example, of the cantilevered beam. Show where the strain gauges are located for a full bridge configuration. There's plenty of versions of that shown in the lecture slides. Identify each gauge, where it sits on the beam, and also where each of those numbered strain gauges are located on the electrical circuit, the Wheatstone bridge circuit, and show the input and output voltage terminals. Now, think about for the case where the beam is downward loaded by a tip load. I want you to when that happens, just indicate on the beam and also on the electrical circuit. You're going to have those two sketches on there. Right? You're going to have an isometric sketch of the beam and a Wheatstone bridge sketch side by side, and indicate which gauges on the beam and on the circuit are in tension, which are in compression. Okay, that's just again having a good physical understanding of what's going on, and that's your pre-lab problem 3. The last pre-lab problem is about using the relationships for the gauge factor and for the full bridge to estimate what kind of voltage output you'd get. And there's 2 separate problems here I want you to submit answers to. In the first case, you have a beam, full bridge, cantilevered, as in the previous problem, and it's got a balanced output. Remember what that means? It means when there's no applied force, it's unstrained, the output has been nulled, right? So you have perfect, that means that the resistors are nominally at values such that you have a null output. So under a certain load, the strain gauges on the top and on the bottom are going to have 5 microstrain, but on the top, each gauge has plus 5 microstrain, on the bottom, negative 5 microstrain. So I want you to calculate the output voltage when that strain condition is set, and here are the parameters for that. Assume the input voltage is 8 volts and so on. Okay, that's the first one, and the second one is, consider that same case, but it's balanced, but now instead of being loaded, the temperature of the beam changes, right, from the environment. And this causes the resistances of each gauge, that's a total resistance, right, to decrease by a factor of 10%. So there's no strain in the beam, but there's a temperature change. What happens? Show what will happen to the output voltage in that case. Explain that. And that's your problem 4. And that's the 4 pre-lab questions that are due before lab. Now, when you go to lab, the basic idea is you have certain objectives. You're going to be setting up the lab. The TA will help you with that. Set up the strain gauge beam, run calibrations, test for force measurement. Use a displacement sensor of some type, either a laser displacement sensor or an LVDT or both. And then you're going to be using LabVIEW and some data acquisition equipment to make measurements, to build static calibration relations, both for the force voltage relation for the beam, and also checking maybe for your displacement sensors. And at the end of the day, you're going to be taking some data that will allow you to estimate the Young's modulus of the aluminum beam. And so when you look at the lab evaluation questions, you're going to be submitting answers to 3 questions. The first one is, I just want you to relate to the TA the calibration relation for the beam sensor. You want to make that based on at least 5 measured points. So I have a little typo here. I should fix this. This says develop a calibration relation for the beam sensor based on all these 5 measure points. And that beam sensor relation is not force versus deflection, it's force versus voltage, right? Because you're going to be measuring voltage from the beam sensor and that gives you force. So the data should be recorded again for this LE in both tabular and graph form. And also, you want you to report your measurement sensitivity or your calibration factor. And see, that's in units, the slope is in units of newtons per volt. So that's why this should be force versus voltage, not deflection. And that's the first one. And then the second one, the TA will give you some unknown weights. You don't know those weights. You're going to measure the force applied by those weights on the tip of your beam. And you'll see, what kind of error you get. And you see how good your calibration is. Okay, that's your second one. And that's kind of the TA testing your calibration skills. And then finally, using your measured force displacement data, you're going to be estimating first the beam stiffness. And remember, we have a theoretical value for that. This is the value that you'll estimate from making force and displacement measurements. And then from that estimated stiffness is how you can use that theoretical formula to extract an estimate for the Young's modulus E, right, given that you've got the other measurements and your data. Okay. So that is your 3 lab evaluation questions, and I am going to close it there. Thank you.